the audio. There we go. All right. So we're back for part 2 of second order or higher, homogeneous, linear order, linear differential equations with constant coefficients. So basically, so section 4.3. So on the first part, I was saying we just have 2 more examples to look at. So we kind of went through that first part. We went through your 3 main examples, kind of covering the 3 possibilities you would find for second order equations, where you end up with your auxiliary equation, or that, the equation you end up solving for 0 is a quadratic equation. And again, like we were talking about, makes sense. It just mirrors solutions to a quadratic equation. You either get 2 solutions, 1 solution repeated, or no solutions, which is really 2, complex solutions. So those were all second order equations, but obviously the point of this section is not just to say we can do this for second order equations, but we can do this for third order, fourth order, etc. So we can do this for equations of higher order. So for instance, so let's say we had something, sorry, look at the number on this. So this is one of your the exercise in the book, number 15. Triple prime, that's 4y double prime minus 5y prime equals 0. So again, still homogeneous, still linear. Constant coefficients are going to guarantee that for you. But definitely higher than second order. But notice that because it's still homogeneous, still constant coefficients. So if we think about solving this, or at least your bet is that, or my bet is that it's still the same setup, right? Because I still need some function that when I take derivatives, I'm getting that same function, or all the derivatives are the same type of function, so that I can get, I can combine like terms and things can cancel out and I end up with a 0, right? So with this, it ends up, doesn't matter if it's third order, fourth order, it's no difference. As long as it's homogeneous, as long as it's constant coefficients, as long as it's linear, then exponential functions are the only functions that make this happen, where you take derivatives, but you still get an exponential function, and therefore things will cancel out as you add and subtract them together. So it ends up with this. Solution is still y equals c e to the mx. Or the solution, my supposed solution is still this. The difference here really is just, now that I got a third order, I'm going to have to go ahead and get the third derivative going, right? But away from here, then it's still kind of the same. So I need to figure out y prime, to figure out y double prime, I need to figure out y triple prime. You guys got very used to doing for those first 3 examples, so I know this is no problem for you guys. Have to go on from the second derivative and do a third derivative. So I'll go ahead and have you guys do that really quick. So pause on your side, I'll pause on my side. Go ahead and get all 3 of those derivatives going. All right, so then for y prime, what did y'all get? should be Cm to the mx. And then for y double prime, what did y'all get? So we multiply by m again, and we get Cm squared e to the mx. So then, gonna follow the pattern from there for the third derivative. Should be Cm cubed e to the mx. And we saw with the last three problems, so with the last three problems, when we plugged our derivatives in, saw that essentially you just end up factoring out a common factor, and what's left over, what's the other factor. It kind of made the remark that it really is just this equation with derivatives replaced with powers. So my question to you guys is, does it seem like the same thing is going to happen here? Yes, good, obviously. So that's the thing that you can expect with these that keeps happening, that is happening just because of the algebra of it. That, essentially, when you're solving this, you're going to end up with this auxiliary equation always that looks exactly like it, just powers instead of derivatives, right? And it's specifically, though, because of this choice of function to begin with. It's the e to the mx. Now, again, this works for this equation, for homogeneous linear equations with homogeneous linear equations. If it was, so again, later in the chapter, we'll get to some other types of equations where that assumption wouldn't work, right? But it works beautifully for this one. So just know to expect that. So at least, to save yourself some time, also to make the logic and connections that you need for these problems. That you're really just going to end up with the same equation, but powers instead of derivatives, right? So let's do that. This is so when I plug this in, we end up with Cm cubed e to the mx minus 4Cm squared e to the mx minus 5 C M 5 Cm e to the mx. And really matter here. And then we factor out a common factor, which is going to be C e to the mx. Yes. That leaves us with m cubed plus 4m squared minus 5. Sorry, this all equals 0. This all equals 0. Then what I'm looking at, again, we know that C e to the mx can't equal 0. The only thing that can equal 0 is this. And then, so this is what we have to solve. 5m. So 5m. Good. But now we're not solving a quadratic equation, but notice that we're just solving a polynomial. So we're now just got in this case, a third degree polynomial set equal to 0, but we're just solving the polynomial. So on these higher order equations, really, we're not doing anything different here. We're not doing anything different than you've ever done in college algebra. So I guess my point out of this problem, or at least at this point in this problem, is these problems are just asking you to solve polynomials, right? Set them equal to 0 and solve them. So whether it's quadratic formula, whether it's factoring, so you're basically on the lease, you're on call for any of the factoring you've ever done, basically in a college algebra class or a pre-calc class. So just know, like, that's where this is going. But you guys are differential equation students. You guys have done this stuff a ton of times, and you're good with it. But just know that that's what it's calling for. You're kind of on call for all the factoring you've ever done. But it's all easy to do. Good. So that's just, again, in general, the problems that you're going to look at once they're above second order, it's just solving polynomials. All right. So notice then, Since this is a third degree, it doesn't, third degree equations don't always have three solutions, but you could have up to three solutions. So one thing to note out of this is that instead of just getting maybe two solutions at, like we saw in the first three, you could possibly get three solutions here. And if this was a fourth derivative and therefore a fourth degree, could possibly get four solutions. So again, so not only know that you're on hook for all the factoring you've ever done, but just know then, kind of expand the possibilities in your mind. Or your general solution here. Your general solution now could not just have two parts, but it can have three parts or four parts, or however many parts you really get from the factoring and solving that you're doing on this auxiliary equation, on that polynomial. All right, but the play from here is exactly the same then. Go ahead and factor this. Set your factors equal to 0, solve them, and then plug those in, and that'll give you, that'll give you the parts to your solutions, and then you can write your general solution overall. Let me have you guys do that. Go ahead and pause on your side. I'll pause on my side. Go ahead and finish this out. All right, let's see where y'all got. So factoring this, there's a common factor, so that comes out, so it'll be m squared minus 4m minus 5, and then hopefully you solve from there, you can factor that further, so m times m minus 5 times m plus 1. Then each of these, then you set equal to 0 and you get a solution. So we get three different solutions out of this. M equals 0, equals 5, equals -1. And these give you your three parts to your solution. So y equals C1. So possibly a different constant for each one of my possible solutions. So C1, so e to the 0x. Realize that's just a 1, basically, right? So so actually our first part to the solution is just C1. The second one is y equals C2 e to the 5x. We also have y equals C3 e to the -1x or -x. So then how would we write our general solution? So our general solution is y equals C1 C2 to the 5x plus C3 e to the -x. That is our general solution, family of solutions. So you'll see some problems like that where, again, just the emphasis here, I'm saying it over and over again, and I'm sure you guys got it. But just once you get up above second order, just like once you got above second degree with your polynomials, just expect all possible types of factoring that could come into play. Your solutions now are going to have likely more than two parts of your general solution. Just leave everything on the table, let it be as it is, just work the algebra and let it tell you what the answer is. All right, then I do want to look at one more. So that actually, I mean, that handles anything you're going to see, but I do want to look at one more problem. I want to look at a problem with initial values. So we did initial values pretty early on, initial value problems pretty early on next week. And then I didn't do any in the subsequent lectures because once you plug the numbers in, it was just algebra, right? So I'm not trying to rehash you guys on algebra. So it was easy for y'all. I could trust that you could do it. So those were, but last week was, we were doing first order differential equations. You'd end up with one solution. So your initial value was usually basically one ordered pair. They're essentially telling you one ordered pair, however they give you the information. And you would plug that information in, solve for your unknown C value, and you would go. So I want you to think about, before we move into the next question, I want you to think about, like a solution like this, right? Or a solution to one of the problems yesterday. The problems yesterday, or sorry, yesterday, but yeah, in the first part of the lecture, you had two parts in general to your, hold on, sorry. Uh, Two parts in general uh, to your general solution. So notice that the ones that you saw in the first part of the lecture had two parts to the general solution. So you had two different constants that were still unknown. This one has three parts. You have three unknowns. So I do want you to, so the reason I want to look at initial value problem now is now they're going to have to give you more information. So again, with first order linear differential equations or first order differential equations, you had, you know, again, highest was first derivative. You had one solution, one unknown constant. So you needed one bit of information to solve for that. But now that we have either two or three unknowns, unknown constants, you can guess then that we need two or three bits of unknown information. So these problems, I want to do one of these just because they're going to have to give you more information actually to solve these initial value problems. And I want you to see maybe how they're going to give you that information. So let's look at one. Let's not go crazy. Let's look at something like 32. 32, they're going to ask you to solve this differential equation. And what they've written. 4y double prime minus 4y prime. It's 3y. 0. So there's our differential equation to solve. Again, homogeneous near second order in this case. So we expect at most two solutions, or we expect two solutions to make up our general solution. In addition, they're going to tell us these bits of information. They're going to tell us that y of 0 equals 1. The interesting thing is you'd figure they would tell you maybe just be another. So going back to thinking about something like this previous problem, and let's say you then have to figure out these three C's. You would figure that they would just tell you sort of three values for, say, for your original function. Y of 0 equals 1 and maybe two others. And actually, well, let's think about this. That is actually technically one way you could do this. But what they're going to give you here is actually, so usually in an initial value problem, not only in these books, but I think just practically in a physics class, chemistry class, something like that. Information they're going to give you here is more likely what you'd see. So instead of giving you just three, essentially, again, this is an ordered pair. So instead of giving you three ordered pairs on the initial, um, the initial function, they will do the following. They'll tell you that y of 0 equals 1, and then in this case, they tell you that y prime of 0 equals 5. So more often what you'll see for initial value problems on higher order differential equations, second or third or fourth or whatever, is they'll actually tell you another order pair that corresponds to one or more of the derivatives. But let's run it through that. So ideally then this problem should pretty much work the same. You just got to solve this, and then we're gonna same as initial value problems you've been doing, and then we're gonna use this information to use this information to go ahead and go back and figure out the C1 and the C2 values. So actually give me a second really quick and we'll jump on this problem. All right, so like I said, this should play out exactly the same. So you get your general solution, and then like we've done with initial values problems, then start using this information to figure out um call it a sorry to figure out your C1 and your C2 values. So that's what I'll have you guys do is I want you pause on your side, I'll pause on my side. First, I want you to go ahead and figure out the general solution. Then we'll go through that, and then we'll start looking at plugging these values in to figure out the constants. Let's do that first. All right, so easy enough. Again, so like I mentioned too in the first part of this video, at some point you can see that, again, this equation that we end up with that we set equal to 0, they call it the auxiliary equation. You can basically read it from this. So again, if you're doing that and not doing the rest of this work, the rest of this initial work, that's fine. That's perfectly fine. That's what you should be doing. But if you can't see that, or if just you still need to kind of do this work to sort of for your head to confirm that everything works out, keep doing that as well. So I'm going to write out, I think a bit like I said on the last example in the first part of this lecture, I'm going to write it out just to kind of write out all the things that I should to kind of show everything clearly. But just know that if you already see that pattern and you just write the auxiliary equation and go from there, then keep doing that. You're good. But y equals c e to the mx, y prime equals cm e to the mx, y double prime equals cm squared e to the mx. So what we get then is 4 cm squared e to the mx. Sure this is factorable. I'm hoping this was factorable. I didn't intend it not to be. Give me a second. Crap, hopefully this is factorable. Damn it, I meant for this to be factorable. Okay. Well, okay, it's at least not complex numbers. I just didn't want to deal with that algebraically. Okay, good then. 4cm squared e to the mx minus 4cm e to the mx minus 3c e to the mx equals 0. So we end up with c e to the mx times 4m squared. It's 4m. It's 3, 0. Set that part equal to 0. factoring on that, let's see, -4. Yeah, that should be factored. How that work down here? Should be what, 2m, 2m -3 +1. That all good, yeah. -6 + 2 is -4, beautiful. So this gives me then two solutions. M equals -1/2. M equals 3/2. Which gives me two parts. Y equals C1 e to the -1/2 x. And y equals C2 to the 3/2 x. Line those together, my general solution is y equals, give myself a little more room here. And my general solution is y equals C1, the -1/2 x, plus C2 to the 3/2 x. Alright, so that's our general solution. Now we know for initial value problems, then what they're looking for is an exact solution, or the, I won't use the word particular, that's for something else, but an exact solution. So we need to go back in and use this information now to kind of plug in and um, get C1 and C2. So again, to go back to the point I was kind of initially making at the beginning of kind of presenting this problem, you have two constants you got to find. You need two bits of information, right? So that's why we've got y of 0 equals 1 and y prime of 0 equals 5. So again, the reason I wanted to show this problem is just that I want you to see the play out of really this part, that there's a little more happening here than there was in the first chapter with first order linear differential equations. Because in the first chapter, it was one unknown constant, only needed one bit of information. And honestly, it was just normal, really easy algebra. And this will still be normal, easy algebra, but it will just be a little more of it. All right. So first thing is, I mean, we can go ahead, notice that, so this is a solution for y. Go ahead and plug in 0 here for x. And let's see what happens. So 0 for x and 1 for y. So I'm saying I'm gonna plug in 1 for y, and then I'm gonna go ahead and plug in 0 for x. When I plug in 0 for x, so we have 1/2 times 0 there. And the x is supposed to be up there. To the 3/2 times 0 there. Notice -1/2 times 0, 3/2 times 0. What are those? 0. Good. And what is e to the 0? That's just a 1. So what we end up with out of this is 1 equals C1 plus C2. C1 plus C2 has to add together to give you 1. Now, hopefully this then is giving you good flashbacks on solving systems of linear equations out of college algebra. So again, in college algebra or just any of your previous classes, when you needed to find multiple constants, you knew you needed multiple equations. So that's really the key here is to find two constants, I need two bits of information, and those two bits of information should create two equations for me, because to find two unknowns, I need two equations at least, right? So that'll help us kind of figure out where to go with the problem, because this tells me, so this says 1 = C1 plus D2, but with just one equation and two unknowns, I can't figure them out. So I need a second equation. So then you gotta kind of, again, critical thinking, just kind of solving your way through the problem. Where is the second equation gonna come from? The information they give me is y prime of 0 = 5. So the second equation is gonna come from this, but notice that I can't plug this into y, I have to plug this into y prime. So this is my general solution for y. So the interesting thing here is, again, I'm not saying this y prime over here. So, because by the end of the problem, we have an actual general solution. We have an exact idea, or an idea of the actual solution to this differential equation. So I'm not saying the y prime over here. What I'm saying is, now that we know y, we're gonna need y prime. We can figure out y prime from this. And once we have y prime, then we can plug in 0 for x, 5 for y, and that's gonna give us a second equation. So, just that similar procedure should give us a similar result. So we plugged in 0 and 1 and got one equation here. Once we have y prime, we can plug in 0 and 5, and that'll give us a second equation. That's kind of the next thing, is we need to figure out, if this is my general solution, I need to figure out my general first derivative. What's y prime? And I want to give you guys a second to do that. So actually, I'm not even going to pause. I want you guys to take a second. I'll pace back and forth, or maybe play some music. I don't know. But I want you to take a second, and this is my general solution. Go ahead and find the first derivative.
Incredible. Great game so much. And your exercise at the gym 3 days a week. Getting on better with your associate employee cutting opportunities. Ladies, eating well, rifle with kids, exaggerated bats, a patient better driver, a safer car, babies friendly backseat, sleeping well, no bad feeds. Paranoia, careful, all animals, never moshing spiders, done up in contact with old friends, and toilet break no pandemic. Frequently check ready action. Favors for favors. On nine month. There is standing orders. On Sundays meeting for some paper getting. Less chance of illness. Tires that rip in no nothing. Starter babies wrapped in backseat. Still cries and a good film. Still kisses with saliva. Longer empty and frantic. Like a cat. Tied mistake. That really maker shit. Evenly to laugh and weakness. Calm. Bitter. Healthier. Cage. Antibiotics.
All right, so what did you get for the first derivative here? And you basically just kind of multiplying down by the coefficient there, so end up with -1/2 C1 e to the -1/2 x plus 3/2 C2 e to the 3/2 x. And then, like I said, you're just basically copying procedure here so then you're gonna take, again, 0 for x. Now that we have y prime, 0 for x and 5 for y, so now 5 equals -1/2 C1 e to the -1/2 times 0, etc. You guys kind of get what's happening here. Halves times 0. Again, anything 0 times 3, the 0 times 3 halves and 0 times -1/2 is 0, e to the 0 is 1. So what we end up with here is 5. Says 5 equals -1/2 C1 plus 3/2 of C2. And now that we have two equations, so again, one equation, one unknown, can't solve it. But now that I have two equations, easy peasy, we can just solve a system of equations from here. And so that's the kicker. That's the difference in these problems, maybe compared to your initial value problems in the first chapter. That more constants to solve are going to require, one, more information. Two, then that means you're solving a system of linear equations rather than just one equation. But again, hopefully, I mean, you guys easily see it. Logically, that makes sense. That's what it would have to be. In this case, two unknowns, two equations, 2 bits information, two equations. So then that's my challenge to you guys, is to go ahead and take these two equations and set it up as a system of linear equations and solve it. So I'll pause on my side, you pause on your side. Let's practice some good old algebra. So take some time and see if you can solve it, and then we'll come back on it. Let's see what you got. Let me also. This camera. All right. right, so we need to slap these two equations together and solve the system. Let me take ability. Let me just go ahead and take that up here. So we have C1 plus C2 equals 1. We basically have -1/2 C1 plus 3/2 C2. 5. Okay. A lot of different ways to go about this. Probably the easiest way is to go ahead and multiply this top by 1/2. So that way you'll have 1/2 C1, which cancels out there, so those will cancel out. But yeah, so then you'll end up with 1/2 C2, and you're gonna add that to, well, let me just go ahead and write out the top first, just to see everything there. 1/2, and I'm combining that with -1/2 C1 plus 3/2 C2 is 5. Those cancel, so we end up with 1/2 and 3/2 is 2, so 2 C2 equals what, 5.5, so that's really 11/2. We divide by 2 on both sides, and we end up with C2 equals 11/4. Once we have C2, we can go back and plug it into either one of these equations, figure out C1. Easy enough. So obviously the top one is your easiest play. 4ths equals 1, which is 4/4. So then I subtract. What I end up with there is C1 equals -7/4. So this, plug these back into my general solution, and I have my exact solution for those initial conditions. So my exact solution is y equals -7/4. A -1/2 x plus 11/4 e to the 3/2 x. And you've got it. Okay. All right, good. So something like that gets your solution when you have initial value conditions for these higher order differential equations. All right, and that's good. So that finishes everything you need for 4.3. And really quick, you'll see kind of the next, we're going on to section 4.4. Next lecture. And you'll see. You'll see really, actually, so to foreshadow or maybe to take the gas out of the next section, you'll see the difference actually is we are going to look at the same thing, except for the right side is not going to be 0. Right side is going to be some function. So we want to look at how do we solve these differential equations when the right side is not 0. So we will figure that out. See you guys for the next one.